Hi everyone, I am Laura. I'm a Schmidt AI and Science Fellow at the University of Oxford. First, I'd like to thank the organisers for inviting me and for organising this exciting event. So I'm going to talk about how we can quantify uncertainties in Earth system models, specifically those that use machine learning, but hopefully some of this might apply to more general Earth system models. So the motivation is that we've seen machine learning coming into lots of different types of weather and climate models. And one type is through hybrid GCMs, which I use to refer to the types of GCMs, general circulation models, that combine physics for the large-scale dynamics. So we keep our dynamical core, our physical model, with machine learning for those small-scale processes, which we usually refer to as parameterizations. So the idea is that we can gather some data, high-resolution data, for example, that's quite expensive, still coming from a model, or you could even use observations. But you have this expensive data set, you can train a machine learning model to capture the small-scale processes, and then you can apply that in a coarse resolution climate model. And then you can run your coarse resolution model much more cheaply, but hoping to get a similar accuracy as your high resolution model. So you can either target particular small scale processes like convection, clouds, and so on, or you could attempt to combine all of the small scale processes into one parameterization, and that's what we'll be doing today. But this kind of approach led me to wonder, well, whenever we're developing parameterizations for climate and weather models, usually we think about uncertainty quantification. So how should we consider uncertainty quantification for these types where we've got machine learning in the place of the parameterizations? And I'm interested in this across both weather and climate timescales. So because we're taking a machine learning perspective, we're going to break down the uncertainties into epistemic uncertainty and aleatoric uncertainty. And I want to think about how we usually use what we usually think about in terms of uncertainties in like climate and weather modeling. So epistemic uncertainty refers to uncertainty in our model. So it comes from lack of knowledge. So this will be incorrect model structure, poorly constrained parameters, or apply when you've trained your machine learning model on one data set in a specific regime, and then you're applying it in a different data set, the different regime. So things like climate change. And usually we want to try and reduce this type of uncertainty. If we have more knowledge or more data, we can try and reduce our epistemic uncertainty. So this is very much what we would usually refer to as model uncertainty or parametric uncertainty in climate and weather modeling. On the other hand, we've got aleatoric uncertainty. So that comes from randomness in your data. So this is coming from initial condition uncertainty or internal variability. Okay, so in parameterizations specifically, epistemic uncertainty is usually referring to the uncertainty in your parameters, and in the physics-based world, this is usually things that are associated with whatever parameterization you're looking at. So it might be like efficiency factors or entrainment rates or something like that in convective parameterizations. And to deal with that, we usually use perturbed parameter ensembles. So we ask an expert what they think the parameters should be, and then we run ensembles with different parameter values and evaluate the uncertainty based on that. And we then also use that information combined with some observations to try and reduce the parametric uncertainty through tuning or calibration. So when it comes to machine learning, if you've got machine learning in your parameterization, we should be able to do something quite similar. The only difference is now our parameters are parameters of our machine learning model. So in a neural network, this will be the weights and biases. So they may be less meaningful than physics-based parameterization. For aleatoric uncertainty, if we think about that in terms of parameterizations, what we're usually thinking about is uncertainty that comes from subgrid variability. So if you are developing a parameterization for a coarse resolution model, you are trying to learn some function that captures what's going on at the high resolution. And the standard approach is to learn some kind of function based on mean grid box behavior, but this isn't always a one-to-one mapping. So you can imagine you could have some high resolution state where all of your states look similar to each other, and you take the mean of that, or you could have a different set of high resolution states with high subgrid variability, but the mean might be the same. So that's what I mean by subgrid variability. So taking the mean isn't always the best in terms of, this is a deterministic parameterization. It doesn't capture subgrid variability, and that's especially important for things like precipitation, where extremes really matter. So in weather modeling, we quite often use stochastic parameterizations to capture this, both in standard physics-based models and in machine learning models. So we're going to look at trying to quantify and break down uncertainties both into epistemic and aleatoric uncertainty in an idealized model. And we're going to use the Lorenz 96 model. So you can think of this as flow or advection around a latitude circle in the mid-latitudes. So it's very idealized. We just have this simple equation here, but we hope we can try and learn from it and learn something about the real weather and climate system. So advection around this circle looks something like this. But really, this is a one-layer system, so we need to include the high resolution as well. And if we do that, what we do is we end up with two coupled equations. So we've got the large-scale variables and then the small-scale variables, which are kind of meant to represent the high-resolution state. So what we actually include in the model, so this is what it would look like. The high-resolution variables in blue, kind of, they're coupled to the low resolution, and they work together. But really what we want to do is replace that high resolution term. So we want to learn a machine learning approximation so that we no longer need to include the high resolution and we can still capture everything at the low resolution model. So this is where machine learning comes in. So the inputs to the machine learning model in this case are the large scale variables, x. The outputs are the effect that the small scale variables have on the large scale. So we're not directly modeling all the small scales, we're trying to capture the effect they have on the large scale. So you can plot that and you can fit a deterministic function. Here we use a small neural network with about 300 parameters. It's just 2 layers, so it's quite simple. But obviously it's not going to be capturing this variability, which comes around from the fact that it's not a one-to-one mapping between inputs at the large scale and the outputs, which are the effect of the small scale variables. So to include that we want to include that variability, and we also want to capture the uncertainty coming from uncertainty in our model. So to do that here, we have been working with a Bayesian neural network. There's various approaches you could take, but here we are basically going to be acting like, instead of our parameters are single values, so by parameters now I mean the neural network parameters, so weights and biases. Now instead we want to learn these and pretend that they're probability distributions. So we want to learn the entire probability distribution for every weight and bias of the neural network. And that then gives us uncertainty in our parameters. For the aleatoric uncertainty, we're going to be treating the data as if it comes from a distribution. Now here we assume it's a normal distribution. So we, instead of learning one output, we learn 2, the mean and the variance of that distribution. So that looks something like that. That's capturing the subgrid variability. And now if we go back to our plot of inputs against outputs, we can put uncertainty bands on there. So in green, we have the aleatoric uncertainty that captures most of the subgrid variability across the data set. And now in purple, we've got the epistemic uncertainty, so that's the model uncertainty. And you can see that's really narrow in the middle where we've got lots of data, but as we move towards the edges of the data set, it increases. So in the low data regime, we've got higher model uncertainty. So really we want to put that back into our model if we want to think about how we use this in the real world. So if we go back to our equation, we now don't have the small scale term, and instead we've replaced it with a parameterization, which is that machine learning model we've learned. And because we're trying to capture uncertainties, we are going to be sampling. So each time we run this, we'd get a different result. So we want to run ensembles to capture uncertainty. And we either sample the output and keep the model parameters fixed to capture aleatoric uncertainty, or we keep the outputs fixed but sample the parameters to capture epistemic uncertainty, or we can do both. And importantly, we also had quite a lot thinking about this, like how should we sample things? Should they be correlated in time? We think, yes, they should be correlated in time if we're thinking about the subgrid variability. So we did that in line with previous weather studies that use like an AR1 approach, autoregressive approach, to sample so that you're consistently keeping some correlations in time or some memory. And then for epistemic uncertainty, we just sample once at the beginning of the simulation and keep that fixed so that we're capturing the full model uncertainty in our simulations. So here's an example of what the online results show us. So we're looking at single variable and how that changes with time on the x-axis. And you've got the three different cases, so aleatoric or data uncertainty, epistemic or model uncertainty, or sampling both at the same time. And you can see the key thing to note is that you really need aleatoric uncertainty in order to capture the truth. So the epistemic uncertainty is quite a lot smaller and doesn't capture the truth as well. This was just one forecast, but we've put this across multiple different forecasts with different initial conditions. And the thing that we're looking at here is, does the model spread correlate with the error? So the skill or against spread. So on the x-axis, we're going to look at ensemble spread, and on the y-axis, we're looking at the error in the ensemble. And ideally, you want that to line up along the y equals x line. And so here's a bunch of simulations with time. You can see that they do generally line up along the y equals x line. But the epistemic uncertainty is quite a lot smaller. So you can see aleatoric uncertainty is really the closest to using both. So I'm just going to summarize that in a summary plot here. The grey line shows the spread for both, and the green line shows the aleatoric uncertainty. So what it looks like is that on weather timescales, so this is 10 days around here, we can probably ignore the influence of epistemic uncertainty in this type of model. And we do need to really test if that applies in real GCMs, but in this idealized model, on weather timescales, we can focus on capturing aleatoric uncertainty. So that's actually quite reassuring because that's already what we do. We do sample using stochastic parameterizations in physical weather models without using machine learning, and also those that do use machine learning, even in full AI models. So what about climate? When we're assessing climate, we need to think about a different approach because we don't look directly at skill on long time scales. So in the Lorenz 96 model, what we look at is breaking down this flow around a circle into two different regimes based on the waves. So you can think about the pattern that you've just got 8 points in this regime, and actually, so this is it's actually periodic, so this would join up with here. But you can have either a kind of wave number 1 pattern, which would be like that, or a wave number 2 pattern, which is in most of the time, so like that, where we've got 2 waves. And we're going to use that as a kind of proxy for a mode of variability that we would use in the climate system. So on this plot at the bottom, you can see most of the time it spends in wave number 2, but it does occasionally jump into wave number 1. So think about this as being like a proxy for something like the North Atlantic Oscillation or the El Nino or the QBO, some kind of oscillation. And remember that the machine learning algorithm was trained on instantaneous subgrid scale values at a single variable, at like 1 pixel. It doesn't know anything about its neighbors, so it doesn't necessarily know that it will be capturing this spatial structure. So does it capture these regimes once coupled online? So what we're looking at now is how often it jumps into this wave number 1 regime over a long period of simulation, so out to 15 years. The black line shows us the truth, and there's a bit of uncertainty in that because if you start from a different setup, you might be in a different regime for a different amount of time, so that's what the grey shading shows. But this black line is the truth, and you can see that the ensembles that sample aleatoric uncertainty, so subgrid variability, that's this green line, they're really focused, they're quite narrow, but they're slightly wrong. So they're overconfident and slightly wrong. On the other hand, you have the purple line, which is epistemic uncertainty only, so model uncertainty, and that is quite a lot broader. We found that basically it depends on your model parameters which regime you end up spending more time in. So it depends quite strongly on that. And then grey, where we sample both at the same time, is a bit of a compromise between the two. So none of these are actually great, but what can we do with that? So we wanted to take an approach that we would usually do in climate modelling, which is to try and then constrain our model parameters. So usually this would be constraining our physics-based parameters, but now we're constraining parameters of a neural network. So this is what we would call calibration or tuning. So we've taken quite a simple approach where after just 3 years of the simulation, we pick the ensemble members that agree best with the truth coming from the 2-layer model, running the full high-resolution system altogether. And then you can see this grey line here agrees much more nicely with the truth over longer periods of time. So this is quite a crude approach to calibration, but we think that this could be useful when we're trying to then constrain these types of machine learning models once they're coupled inside a GCM. So we think we might be able to use this going forward. So the other thing, so this is the same plot here. Now this calibration was carried out with the fixed climate type simulation. So there was one thing I didn't mention in the equations, that you have control over the amount of forcing that you add to this system. And we can treat that a little bit like climate change forcing. So here our forcing was 20. I mean, the value is meaningless, but we can imagine that's some kind of current climate. And then what happens if we change that? We found that obviously this would then lead the modes of variability to change if you've changed the forcing. And we found that that also improved the behavior of after we've constrained on the previous climate. So when we've changed the new climate state, we find the calibration has helped us with that as well. But what would be even better would be if you actually constrained based on your new climate state. So hopefully that helps us with constraining simulations as we move towards a warmer climate. So just to return to the question of how should we consider uncertainties in hybrid GCMs, we've been thinking about this and we've come up with this approach to use a Bayesian neural network to capture uncertainty in parameters in a very similar way that we would usually do for standard physics-based parameterizations, and then also capturing the uncertainty from the subgrid variability, so aleatoric uncertainty. And we've set this up in this idealized toy model using Lorenz 96. But really we need to know now, does this hold in a full GCM? So we're looking at implementing it in a full GCM and investigating whether we can do the same approach. So what we think we might find is that aleatoric uncertainty dominates on weather timescales. So if you're focused on weather, we could focus on just capturing the subgrid variability. But on climate timescales, we need to consider both epistemic uncertainty and aleatoric uncertainty. And that can really help when constraining through calibration as well. So next, we're working on implementing this in a full GCM, and I'm very open to suggestions and ideas of where we could go next in terms of thinking about dealing with uncertainties in hybrid GCMs or in any kind of climate model. So yeah, thank you very much for your time.
Given the time, we do have a bit of time for questions now, if there are any, before we move to the lightning talks. Yep.
Can I ask a question about one of the last slide, when you are the constraint and you get and you show this it's getting much better. But if I want to understand you constrain on both, so have you seen what happens if you constrain on just one, say aleatoric or epistemic only?
Yeah.
So the question is, do you need both plus the constraint, or you might need just one, aleatoric epistemic plus the constraint?
Yeah. So actually you can't constrain on the aleatoric uncertainty, because what we're actually doing is we're constraining the model parameters, which are modeled by the fact that we're modeling each parameter as a probability distribution. So that is the epistemic uncertainty. So yes, we did compare constraining on just epistemic or on both. And constraining on just epistemic did also work, but we found that it worked a lot better when we constrained on both. And we think that's because including the subgrid variability helped the model kind of move between these different regimes quite a lot more. So in the epistemic, if you just fix your model parameters and don't include aleatoric uncertainty, it kind of got stuck for ages and would move less often. So I think you could either run it for longer, which is obviously much more expensive, or including the aleatoric uncertainty helped the model move around a bit more, if that makes sense. But whether or not that applies in a real GCM, I don't know.
Okay, any other questions? Alexander? Yeah.
So with the epistemic uncertainty, does it matter that you've only considered normal distributions for the aleatoric uncertainty? Like,
it might do, yes. So for the reason for using it for aleatoric uncertainty, we looked at the data in like the diagonal, or in the marginal, like across here, and it looked kind of normal. So that's why we used that for aleatoric uncertainty. But for epistemic uncertainty, I really don't know. So I don't know what the parameters should be. So yeah, we're putting a Gaussian prior on all of our parameters, and I don't know if that is valid. Haven't tested any other alternatives, but that is quite commonly done in this approach. But yeah, it's a good question and could potentially be tested somehow.
Okay, maybe we thank Laura again and then move to the lightning talk.